All right, so the second application that we're going to look at actually is really closely tied to Pascal's triangle, but we're going to sort of take it out of that a little bit. So the next thing we can do, and this is actually something that you might see in computer science where you're trying to find paths through a network or something along those lines, or like the number of ways that you could do something. So we're going to find the number of paths in this, this graph here. And specifically, I'm saying minimal paths here. So what the minimal is going to do for us, essentially, it means there's no backtracking. I need to write that word a little bit nicer. So there's no going back. You basically would only be going downwards. And I guess I didn't really specify this, but you're assuming that you're only allowed to go on those lines in the graph. So it's a pretty typical question. Okay, so there's going to be really two ways to approach this. The first way is going to be a little bit more practical for what we do next. And so I'm going to start with that. So what we can actually do is just sort of work our way through and count the number of ways to get to every single upcoming node in this system. So for example, there's really only one way to be at A, and that's to get that's like you get started. And now let's say I want to move to this point here, just to the right of A. Well, there's really only one way to get there, and that's to come from A, because I can't do anything like, I can't come up this way because I'm sort of backtracking, because for me to get to this point, I'd have to be going back up to get to that one, and that means I'm adding to my length. So I don't want to do that. Now, similarly on the left, the only way to get to this point on the left really is to come down from A. And then where it starts to get a little bit more interesting is when I start looking at maybe the next line of points. So these 3 points here. So this one on the far left, well, there's only one way to get to it, and that's coming from that second row point. And this one over here on the far right, again, I can only go downwards, so I can only come from that one up and to the left. Now, this point here is a little bit more interesting because I can come from these two paths. And we can really only go down the path, so I can only come from those two. And there's one way to get here on the left, and there's one way to get to the right point. So I could either go left, like down left, down right, or down right, down left. So there's 1 + 1 = 2 places there. And then it starts to get a little bit more interesting as we make our way down the next row of points. And so this one, I can really only come from that, to get to that one, I can really just go like left, left, left. This one here, now what I can do is come from that point up to the left. So there's one way to come there, but now there's two different ways to get to this point here. I could go left, right, left, or I could go right, left, left. So there's actually two possibilities there. And so what I'm actually doing is just adding the number of ways that I could get to the previous two nodes. And that's going to give me the total number of paths that will get me to this point. So there's actually 3 here. And then same pattern here, 2 + 1 is 3. And then this one's just 1. And if you're following along, what I'm doing here is really actually just Pascal's triangle. So to get to this far left, there's only one way to get there. To get to this point here, it would be 1 + 3 is 4. This one here, I could take any of the 3 paths in the top left, or any of the 3 paths in the top right. And it's that word "or" that tells me to add them. And so I'm actually going to get a 6 there. I'm just going to move that 4 below to be consistent. And so this one, I could take any of the 3 from the left or the one from the right to have 4 paths there. And then there's 1 over here. And then similarly, I would just fill in the rest of these all the same way. It is completely just Pascal's triangle, which also does mean that I can cheat and get the answer B a little bit differently. And I'll show you how in a second. But yeah, so I'll have 4 + 1 is 5, 4 + 6 is 10, 6 + 10 is 4, 5, 1. 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, 15 and 20 is 35, 35, 21, 70, and then I'm at 56, and then that should be 126. And so that would be my answer, 126 paths. So these are just completely the numbers from Pascal's triangle. And that means that there's a formula. We can actually use that binomial formula from that. But there's actually a way that that makes perfect sense to do so, and not just that that sort of fudgy explanation of using that C formula in that section. What we can actually do is think of this: to get from A to B, basically to do this minimally, I'll add that word here. What we're going to do is go left 4 times and right 5 times. So we go down left, four times, and down right 5 times. And basically every single path is determined entirely by the arrangements of the lefts and the rights. In fact, determined uniquely. Right, so if I did like, yeah, if I have like a path and I swap a left and a right, it creates a different path entirely. So we can actually just count the number of arrangements of lefts and rights. Well, there's 9 total. So remember, this is just this is going to be arrangements with repetitions. So there's 9 total, and then there's 4 lefts. So 4 repetitions of 4 and 5 right repetitions. Yeah, it's like basically arranging, finding the words that are made from 4 L's and 5 R's. It's the same thing. This is exactly the formula. This is just 9C4 or 9C5, whatever you like. It doesn't really matter. So yeah, and that would give you exactly this row in the Pascal's triangle. So if you count down, if this was 0, I'd have 0. If you count the lines across, I'd have a 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So yeah, that would be the 9th row if we start at 0. And that's maybe a little bit harder to see how far we're going across, but it would be either like 5 from one direction or 4 from the other. So yeah, it actually kind of works. It ties things together. So that's one way that you could answer these questions. I'm going to do a different example now where we don't really get to use that formula because there's going to be gaps. For the next question, what we're going to do is find the paths on a graph that maybe has some sort of weird missing pathways to it. So in this graph here, what we're going to do is first of all find the number of minimal paths. So when we say that, we mean we don't want to do anything weird like go down across and then maybe go down and then maybe go backwards towards A and then up and over, or do weird things like that, because we're sort of doubling over the same steps. We're going right then left, so we never really want to do that. So we say minimal paths. The only directions we should be going are right or down in this case. It depends on how the picture is orientated. So yeah, I'm only going to go right and down, and that means that there's some paths here that I can see that are not actually part of it. So these yellow dotted lines here, these don't exist in my picture. My bad, I wanted to actually have a line here. Doesn't matter too much. So just added that little one, but yes, we don't have these paths, which means we can't move in those directions, but otherwise everything kind of follows what we do with Pascal's triangle. Your starting point A, we have one way of starting, and that's by starting at A. And then now if we look, for example, going downwards, there's only one way for me to get to this point here, and that's by going down, because I can't come from the right and I can't come from the bottom. Now this point here, to get to that one, I would either go over or down to get to it. So I need to find the number of ways that I can get up to this point above it, and there's one, just by going to the left. So what I get is the sum of the two sort of previous values, and so I get a sum of 2 there. I usually find it easiest to work in like columns across or rows down. So if I stick with this column, the only way for me to get here is from above, so that's a 1. If there was a node here, I would only get there 1 from above, 1. Basically, there's only one way to get everywhere along that leftmost edge. And then it starts getting a little bit more interesting as we move into the middle. So this point here, now I can have 1 from the left or 2 from above. So there's actually 3 different paths I could take to get to that. We can see those 3 paths illustrated by either down, down, over, down, over, down, or over, down, down. Right, so those are those 3 paths right there. And that's kind of the idea, is that by mapping it this way, we can sort of trace back all those possibilities we've already considered. Now to get to this one, I don't have this path from the left, that's gone. So there's actually only one way to get here, and that's coming down. So that's just going to be the 3 there. And then similar with this node here, I don't have the upwards path that comes down to it, so I can actually only go over. I can only get that one by going over 1. And then same here, I can only get this one by going over 1. So there's only the one way to get there. And now I make my way to the next point in the column, the next column in the picture. So I can only get this one by going over. Now this one below, I can get the 2 from here or the 1 from here for a total of 3. And this one I can get 3 plus 3 is 6. And now this, well, I can get this 3 or that 6 to get 9. And here I would get over 1 and down 9, a total of 10, and then 11. And so basically that's what I'm doing every single time, is actually just adding these numbers. So I get 1 plus 3 is 4. This one is actually 0 because I don't have either of these 2 paths. But now this one's going to be 9, 19. 19 plus 11 is 30. 1 plus 4 is 5. 5 plus 0 is 5. 5 plus 9 is 14. 14 plus 19 is 33. 63. And then just keep making my way. 6 plus 5 is 11. 11 plus 14 is 25. 25 plus 33 is 58. 58 plus 63, I want to say 121. I am going to double check that. Yeah. There's only one way to get here. This one, right, there's no path down, so it's actually just the 6. 17, 42, 100, 221, and 1, 7, 24, plus 42 is 66, 166, and 166 plus 221 is 387 total paths. To try to actually draw all of those paths would be kind of crazy, but this is sort of a semi-quick way of just figuring out what that number is going to be.